So we get back with the basic formulation of the statistical learning theory. I just wrote here the basic inequation we found. So there was a small mistake, my mistake. Like both lectures I used like greater than or equal. Actually, it's just greater than epsilon. There's no equal here. So just to make sure it's recorded so people can see afterwards. So I use the greater than or equal, and it's just greater than. Okay. And instead of using this m, we could use something like m of n, because this is the Shuttering Coefficient. It's a function that grows according to the sample size. But Vapnik usually, or not just Vapnik, but some papers usually refer to this function as n of fn. That means like something connected to the cardinality of the space of the miscible functions or bias in terms of the sample size. That's actually the Shuttering Coefficient, right? But it's just another notation, a different notation for the Shuttering Coefficient, but it's the same. Just to remember again, I said that in the first lecture, all the risks must be in range 0, 1. It's impossible to deal with risks outside that range with this formulation. We can adapt it to work with a different range. It's possible, it's not difficult. If you guys are interested, you can use the Generalization Bound on this side, and you're gonna have some sort of division here. I can show you later, maybe if you are interested. But divided by the sum of differences, and that's also possible if you wish, if it's better for you. I mean, if you have, for example, a situation where you are considering some sort of regression rather than just classification. That would be, of course, better. Okay, so on top of this, I think we could give a next step. My next step will be this. All of this formulation is for a single sample. So I have just one sample and I'm measuring the empirical risk or the risk I have in that sample and comparing that risk or that error, if you wish, if you prefer, to the expected risk or the expected error. The error for the examples, the unseen examples, the examples we've never seen before. We're going to apply our model F in that particular domain and see what happens. That's what it means, basically, right? So there is something quite important here. We can somehow define delta to be equal to 2, our Shuttering Coefficient for a single sample, times the exponential value of -2n epsilon squared. And using that, we can isolate epsilon to find which is the ideal epsilon. That's an important step if you want to analyze a given algorithm or compare your algorithm against several others and have some sort of fair comparison in that sense. So as next step, I will apply the exponential and the log in the Shuttering function, the Shuttering Coefficient, to have something like this. So I apply an exponential and a log function on this guy to have this, times the exponential of -2n epsilon squared. In that situation, I can sum up the powers of both exponentials and end up with this, the exponential of d log of n fn minus 2n epsilon squared. From that, the next step I will give, and this is delta, this is our delta, I will try to isolate epsilon, and that was something that Vapnik did, because after having that epsilon, I could use this inner part of my probability. I could apply my epsilon here and see how it's useful to understand the differences or the divergences we have in between both risks. And that's quite interesting, and that's probably the most important thing, the most important conclusion after the statistical learning theory. I mean, we could talk like a lot about the statistical learning theory, but at the end of the day, the most important thing is this last step. Because all those steps, previous steps, were just to justify somehow this last one. So as a last step, from here, I will isolate epsilon, and to isolate epsilon, of course, I will apply a log on this side. So I have log of delta equals to the log of everything. 2 times exponential of log this guy. So if I do that, what will I have? I'll have, of course, I have the log of a product, so I can use the sum of logs, right? So we end up with something like log of delta is equal to the log of 2 plus the log of this exponential function. And of course, that will help me to take out the log function, the exponential function, sorry. Exponential function. Okay, so here I can remove this exponential function. I'm gonna cancel it out. So we have log of delta to be equal to log of 2 plus log of the Shuttering coefficient for a single sample minus 2 times n epsilon squared. So now we can isolate epsilon. So our epsilon will be something like this. Let's do it like step by step. So we will have like a minus log 2 minus log Shuttering coefficient of the Shuttering coefficient is equal to minus 2n epsilon squared. And of course now we can divide by minus 2n. So we have, just to simplify, I'm going to divide all this term on this side by minus 2n. So I have epsilon squared equals to this term, so I can apply a squared root on this term. If I apply a squared root on this term to isolate epsilon here, I want you to notice that every time if I come back here, I just have the option of epsilon to be greater than 0. Could be equal, but it's impossible to be negative because this is an absolute value, this is a norm, right? So it has to be positive. So as it has to be positive, when I have assessed that squared root, I don't have to look for the negative side, just the positive side. So epsilon is equal to this, term. So from that, that's something, probably that's the most important step. Now I can get that epsilon and apply just side this probability. That's very important, very useful, because now I can understand how big is the difference I have from my model applied in my sample, in my training or test or whatever sample, and compare that to the empirical risk, to the expected risk, sorry, to the risk in the real world, to the risk for never seeing examples, for unseen instances. So from that, I'll just clean up just this part, because now I'm gonna leave this just to remember, because now what Vapnik did was this. So I have this supremum value of f in f, and that's the worst case situation. I think you guys remember from the previous videos and also from the previous lecture, to be greater than epsilon. And that was my mistake. It was greater or equal, but it's actually greater, just greater. So from that, I could apply this epsilon on this side, on this right side, and formulate the differences we have in the worst case situation. And that's something important. And that's something, I mean, now we have somehow to remove the absolute value. The absolute value. How can we remove that absolute value? I mean, are we sure that maybe one of those risks is greater so that we can avoid the absolute value? In fact, yes, we are sure. We are sure that every time we compute some empirical risk, that risk is being computed in terms of our data set. So, of course, in the worst case scenario, is a case where I have the greatest overfit. When I overfit, this term will be probably as close as possible to 0, or as close as possible to some small value. Not necessarily 0, but as close as possible to some small value. And this will be very big. So I'm sure this term will be closer, somehow closer to 1 in that situation, this closer to 0. And if that's not the case, if I don't have like the worst case scenario, if I have some fair situation, even in that situation, as my classifier is being driven by data, that risk will always be smaller. So this empirical risk will be always smaller or eventually equal to the expected risk. So from that, I take this conclusion. I could invert this and have this expected risk minus the empirical risk of f, and this is by definition. This is by definition. So this subtraction must be greater than epsilon. And probably now you know something, you already know, but it's good to remember that this is for the missing cases. What I mean by missing cases or missing situations are the situations our classifier didn't work. Because I'm computing when it didn't work, when it somehow surpassed that bound, that epsilon limit, that divergence, that bound, that threshold. So somehow, if that's the missing, I could look to the other side, I could look to the hitting cases instead, to the cases that somehow we had a good solution. So the cases we had a good solution were when this difference was not greater than, but it was somehow smaller than or equal to epsilon. So this is the hitting cases, or the cases where our classifier has indeed worked properly, whose results were good. So here we had good results according to our threshold epsilon. So in that situation, I apply this epsilon on this side to have a next step and to understand what's happening now. So that's the next situation. So now we'll have something like this. I'm going to clean up just this part. From this, Vapnik formulated what is called the generalization bound. So the generalization bound, and this is for one sample, for a single sample, because there is another bound for two samples. I'm going to talk about it next, right after. So for a single sample, it is the expected risk is less than or equal to the empirical risk plus this epsilon term. And this epsilon term, as you guys can see, it will be like 1 over 2n, the square root of 1 over 2n, multiplied by log of the Shuttering coefficient, plus log of 2 minus log delta. This is the most important result after the statistical learning theory. I mean, after this result, SVM came out. After that result, we were capable of understanding that besides analyzing empirical risks, we have something that's even more important. Because, I mean, we could run perform some experiments using a given technique. And that technique could provide, like, at the last stage, some sort of empirical risks on a given sample. Let's say that sample is the test sample. Okay, in that sample, let's say we have like the multi-layer perceptron with 2 hyperplanes, and you have a multi-layer perceptron with 3 hyperplanes. Let's say that in that situation, this empirical risk was like 0.05 and here 0.01. What makes the difference is the other term, is this next term. So somehow it's unfair if we just analyze techniques using the accuracies we obtained. So the accuracies are a good estimation, of course, but a part of that we should analyze also in terms of the shattering, in terms of the space of admissible functions, in terms of the bias, in terms of the complexity we have for that given model. So here, of course, that having 3 hyperplanes, the complexity will be greater. So somehow this complexity will affect the behavior. If we have lots of examples, this will converge as good as it will converge for this first case. So the empirical risk is enough. But if we don't have enough trainee sample, this will be converging faster. And the second will take more examples to converge. So how can you say that you have some good result just based on some assumption if you didn't assess the sample size, the effect of that given sample size in terms of the complexity we have for that particular algorithm? And so now we have this chance of assessing this term. So in my opinion, now we should go to the next step and understand how this term affects learning. And that's something I will show using my computer. But before that, I'd like to at least to show you which is the formulation for 2 samples. Why for 2 samples? Because having 2 samples, we can understand how that will affect learning without necessarily computing the empirical risk. The expected risk. Without computing the expected risk. Because the expected risk is not indeed computable for real-world problems. How can I compute some risk that depends on the perfect joint probability distribution? You should have access to every input mapped to every output value for a given problem. Actually, if you have that, you could build up a hash table. You don't have to use machine learning for that. Because if you have like the perfect situation with every input mapped to every possible output, there's no meaning of learning something out of that data set. So in that situation, I would like to show you something. I'm not gonna derive that from the beginning, because now I think that's easier to see. Something that Vapnik did was this. From this formulation, from this supreme value of the empirical risk of f to the expected risk of f to be greater than some epsilon, he would like to reformulate that using something computable. In that situation, he observed the result from the lemma of symmetry. That lemma of symmetry, I don't remember if there is a y here. Okay, doesn't matter. I think it is. So the lemma of symmetry tells us that instead of having the difference in between the empirical risk and the expected risk, we can have the differences in between two averages. So we could have like one average here at a given sample from 1 to n, and this would be another average from n plus 1 to 2n, given the same probability, the same underlying probability distribution. And that difference, in terms of this probability, it is, to be greater than some epsilon. That's smaller than 2 times exponential value of minus n epsilon squared over 4. So actually, he used that instead of everything I showed you before. So that was he used, indeed. But in so many papers you read, probably like the paper I suggested to you, that paper by von Luxburg, she don't show like all the steps in between. She just come up with that afterwards. But that was the inequation Vapnik indeed used. So in that situation, he didn't have like just an empirical risk and expected risk. He could compute in that situation 2 empirical risks. A given empirical risk and another, which is usually illustrated with this apostrophe. That's actually what he used. So instead of that, as an upper bound, now you guys know what it is. This would be the Shuttering Coefficient, but not for a single sample, but for 2 samples. So it's not 1n, but it's 2n. So the sample size has doubled. It's not just 1n, but 2 of the exponential value of that. This is the most traditional, this is the most traditional formulation you're going to see in books. So now we already know what he did. Actually, what he was interested was basically analyzing this term. And not just this difference, but both together. There's something very interesting to mention now. Now you see from where exactly the k-fold cross-validation came. That's the k-fold cross-validation. Because if I have a sample, I measure the error there, I measure the error in another sample, and if the errors are both very, very close, that somehow means that my epsilon is not too big. So that's the same as having, okay, I am analyzing the empirical risks, but I am also analyzing the complexity of my bias, or the Shuttering Coefficient. So if I have some sort of error, like the average empirical risk I have for a k-fold cross-validation with k equals 10, for example, is equal to, for example, 0.1, 0.01. Suppose now the shattering, I mean not the shattering, but that epsilon is amazingly big. What would happen? The standard deviation of those risks, of those empirical risks, like for every empirical risk I measure here, will be great, of course. So if I have some sort of, let's say here is like 0.5, that basically means I have some space that's very complex. So a part of having a very good result in terms of this guy, my epsilon is big. My epsilon here is big. So I can use the k-fold cross-validation as a way of understanding not just the empirical risks, but its variance is going to tell me about the complexity of the space of functions, about the complexity of the bias. So as it increases, that means I have more complexity. What could I do? I could have more examples to verify if somehow that will decrease. So if I take some conclusion based on a given experiment that my standard deviation of all those k folds computing the empirical risks for every fold, I have having like a very amazing standard deviation. In that situation, I should conclude like, okay, I don't have a conclusion. I should have more examples because somehow this should be reduced. If it's not reducing, my complexity is too big. It's huge. It's amazing. The most traditional way of showing, of defining the generalization bound is this one. So when you go to books, generalization, when you go to books and papers, this is the most traditional way of showing the generalization bound for two samples. Actually, in this case it's for two, but we can extend for more, of course. And that is usually people, this is actually an upper bound of that. This is like an upper bound of that. So people usually show this term, like the supreme value of f in f, given the empirical risk of f minus the expected risk of f to be greater than epsilon. That's bounded, upper bounded by this probability. So the probability, and that's something that comes after the lemma of symmetry. Actually, it's a lemma of symmetrization. That's the right way of spelling it. F in f, and that's the empirical risk in one sample and the empirical risk in another. That's why this apostrophe here. In another sample to be greater than some epsilon, and that's upper bounded by this Shuttering coefficient given two samples. From that, what you usually see in books is just an analysis on top of this term. So people get this term, and they say, okay, in that situation, the expected risk will be smaller than or equal to the empirical risk of f, and now you know from where this comes, right? Plus, I have to isolate epsilon again. And isolating epsilon, let's see if I'm not mistaken, but I will have for over n, let's see, times log of the Shuttering coefficient for two samples. It is plus log of 2 Log of 2 minus log of delta. Is it that? Can you confirm for me, please? I think it's that. For over n. Sorry. Is it right, or maybe compared to the previous? I don't remember. It's okay? Yeah. Yeah, because now we have like divided by 4. And there's no 2 here. Oh yeah, there's no 2 there, right? So it's not log of 2 here, isn't it? Because this 2, let me see. Let's open. I think it's better. Yeah. If we open it. Okay. So opening, we have delta equals to 2n f2n, because it's a composed by 2 samples. So in that situation, we will have log on this side of delta to be equal of log of everything. So we have log of 2, yeah, perfect. Log of 2, and this guy will be inside. So somehow we will have plus log of n f2n, right? Mm-hmm. Minus n. Oh yeah, I think it was right. Okay, but anyway, we do it again, no problem. So here we have, okay, now we can say log of delta minus log of 2 minus log of the Shuttering coefficient for 2 samples is equal to minus n epsilon squared over 4. And that will be the same as 4 minus 4 over n being multiplied here, right? Mm. Have to remove it from here. Okay? And now we have the the squared root. Yeah, it's right. Mm. So now we can do from this, we finally have the expected risk to be smaller than or equal to the empirical risk of f plus this term. I prefer this term as a positive term because it makes easier to understand what's happening. So I prefer it like 4 over n multiplied by minus log delta. Let's put the things that are positive at the beginning. And the most important thing is the Shuttering coefficient. So the Shuttering to start. Then plus log 2 and minus log delta. Yeah, it's that. So now, the main conclusion we have is we shouldn't be just assessing the empirical risks. We should somehow assess also the complexity we have for the biases. That's very important. But there is something else. Let's suppose that my Shuttering coefficient is exponential. Let's suppose it is exponential. What would be the result if it is exponential? What happens? Let's say it is something like 2 powered 2n. So the ends go away. The ends will be cancelled. Yes. The ends will be cancelled. Here we have log of 2, which is, of course, greater than log of delta. But what's delta, in fact? Coming back, we see this term on the right side was made equal to delta. What that delta means? So just take a look. What that delta means, should mean. if delta is equal, for example, to 0.5, this basically means that I want the probability of having this difference greater than epsilon happening just for 5% of the cases. In 95% of the cases, I don't want it to happen. So this works as some level of confidence. Some level of confidence. That's a confidence level, actually. So when I can see delta as some sort of term that ensures an upper probability. So if I say I want this to happen just in 1% of the cases, this would be 0.01. And if this guy is 0.01, it's so small, when I apply log, right? And I already have, like here, log of 2. What's going to be the result here? It's going to be log of 2 divided by delta, actually. Will I have some sort of upper bound here? No. This guy is not defined. So as it's not defined, will I have some sort of learning in that situation if my space of admissible functions, if my bias is two-way complex? No. I have no way of ensuring it. So if it's too complex, my bias, there's no learning bound. There's no learning guarantee, actually, because the complexity is so amazing. That makes us remember probably the Occam's razor principle. That makes us remember from statistics the parsimony principle, where somehow we should have some balance in between the complexity of the space and the result we have here. I mean, the quality of the result we expect. So it's not just about analyzing the quality, but also analyzing the complexity. Of course, if I use the k-fold cross-validation and I show people the standard deviation, I am already implicitly showing that my complexity is not amazing. But we see many papers where people just show the average. Just show the average of the k-fold cross-validation. Haven't you? Is that fair? I mean, no, it's not. Because I have no idea about the complexity of the space. If the space is too complex or it's not. Could be a simple space. Exactly after that, you know what's interesting? This, if you guys look for the Tikhonov regularization, if you guys look for back learning by Valiant, right? And if you guys look for the random maker complexity, it's the same. So different people in different moments in time found out the same inequality, that we have to have some sort of balance between the complexity we have for the space of divisible functions and the result we have in a given sample to ensure some bound for examples we have never seen yet. But probably we're going to receive those examples, and we expect that our classifier F or our regressor F works well in that scenario. But to have that, it's not just enough to have some good result in a given sample, but we also have to have some space of divisible functions, aka bias, that's not too complex. Something else. And that's only ensured only if my joint probability distribution is fixed, is static. that's only insured, again, I think you remember from the first lecture, if my data is IID. So if you guys think, okay, but I'm gonna use that to learn time series. If you're gonna use data a long time, and it's gonna probably have some sort of dependence, this is not insured. It's not insured. You have to do something else. You have to give another step to make it work, to make it, I mean, you could have good results, but is that meaningful? If you don't do something else, what can you do? Of course, you can apply some sort of transformation on data to ensure data is IID. That's something I've been working a lot, like for the last 10 years, I'd say. And something else, JPD must be fixed. So if my data distribution changes a long time, what means basically is that maybe on this side of the room, I have a bunch of sand, and a long time that sand goes to the other corner. Is it fair to say that I have a good result if I'm just assessing for this pile of sand, and afterwards the sand is not going to be here, it's going to be there, so the behavior is completely different. So I have no bound, no learning guarantee in that scenario too. Again, that's a problem. I have somehow to characterize my data distribution. I have to have a good space. For example, it's R2, R3, R something, or it's not even R, it could be another space, could be a space of integers or something else. But is that space meaningful? Is that space telling me what's happening in that particular problem? After this, Vapnik with another lady called Corina, they worked together to build up the large margin bound. The large margin bound tells me something that's very interesting, very, very, very interesting. And it's so simple to explain. It's so neat. It's this. If I have a bunch of points in a given space, and those points are very far from the negative points, if I build up a hyperplane here, having the largest as possible margin from both data sets, from the positive and from the negative side, this is the margin, or this is the margin if you prefer, because both should be equal, right? Not numerically equal, because there's some, of course, there's some variation when you're computing. You have the smallest as possible Shuttering coefficient. That's the main conclusion of that. I can write down that bound, but what's the most important is that as soon as I found out some space, what I have some data distribution from the positive side and another from the negative side, which are very, very far from each other, I reduce the Shuttering coefficient. If I reduce the Shuttering coefficient, I reduce the complexity. If I reduce the complexity, I need less data to ensure learning. I need less examples to ensure my classifier or my regressor are indeed working in practice. That's so, I mean, yeah, almost time. That's so interesting, right? I'm just gonna write down here something, just remember this. And then I don't even know if we should go next step. I think we could define what we're gonna do next. I think it's better if we do that. for the next Friday. So next Friday, I'd like to discuss with you this, just this. This is an equation. You guys let me know if it's wrong or not. I think it's right, but let's remember it's like log of 2, right? Minus log of delta. Okay, so that's a point. So I can look to that generalization bound. Generalization bound as the best as possible way to analyze learning guarantees, in the sense of classification and in the sense of regression. It doesn't work, of course, for unsupervised learning because this is not unsupervised. You have a loss function to compute the error, so there's no way of using that directly to unsupervised learning. Again, this delta is the same as, okay, here I had the supreme value of the empirical risk as an estimator for the expected risk given epsilon, and this is smaller than or equal to delta. So delta means the confidence level I want to ensure during learning. What's the confidence level I want to ensure? Of course, if I define delta to be equal like 0.5, it's going to be easier. But if I define it to be very small, and as small it is, of course I will have some impact here, right? Because this is going to be the log of 2 divided by delta. And if delta is very, very small, if delta approaches 0 somehow from the positive side, this turns out to be infinite. So I would have like a log of infinite. And that's a problem, right? Indefinite. It's impossible to have that in that scenario. That makes interesting to observe that it's just impossible to ensure 0. It makes impossible. Something else, just a next step. How can I understand if this term provides learning to me? In other words, what's the most important term? We have a square root of 4 times the log of something divided by n plus log of 2 divided by n minus log of delta divided by n. Let's assume delta is greater than 0 because equals 0 would be a big problem, right?